So in our first skill, in our last learning unit here, learning unit 11 on thinking about some more advanced concepts with covalent bonding, in our first skill, we really talked about how we need to hybridize central atoms that are making more than one bond to other atoms, because that is going to allow it to create those equal bonds with other atoms. So in our next learning unit here, or next skill here in this learning unit, we're actually going to take a little bit of a deeper dive as to how those orbitals interact and overlap specifically to make these bonds. So let's just review a couple of skills here to think about how we are going to be forming these bonds, right? So in our last skill here in this learning unit, we talked about how we needed to hybridize orbitals to create equivalent orbitals so that we could have orbitals overlap. And so valence bond theory really allows us to think about how those orbitals overlap. So again, the simplest example we could have here is where we're forming hydrogen gas, the smallest atom, the simplest element that we have here, only one valence electron. No hybridization required. We've got a hydrogen atom with a single electron in a 1s orbital, interacting with another hydrogen atom with its single electron in its 1s orbital. When we bring these orbitals together, what's going to happen is these two electrons are going to live in the space between those two atoms, two electrons making a bond, so this really represents the bond between these two hydrogen atoms here. And as we learned about in our last skill, we have a situation where those electrons have to have opposite spin. And again, we can see that here. Here's some of our rules, just revisiting. We have to have those electrons having opposite spin. We are going to have the strongest bond when we sort of maximize the overlap that we're going to have here between these atoms. So again, having the maximum overlap. Two spheres, it's pretty easy to do. We're going to talk about some of those hybrid orbitals in just a second here. We talked about this concept of hybridization and why we need to sort of have this mixing of atomic orbitals if we needed to generate more than one bond. But again, the situation we have here with hydrogen, there's only one bond that we're forming there. Just like, let me flip back here just for a second. When we talked about forming these bonds here, we needed to have hybrid orbitals with that, in this case, phosphorus or sulfur, between this central atom and these peripheral fluorines. The central atom needed to be hybridized because it was forming more than one bond. If you're only forming one bond, like we have with these fluorine atoms, then we don't have hybridization of that orbital. So again, we already talked about the how and the why and how you get the letters for hybridization, but what we're going to focus on now in this skill is how those hybrid orbitals, or those unhybridized orbitals for that matter, how do they overlap? Okay, and I'm glad I have some video here where you can see me, because two things that I want to highlight using my hands here is we can either talk about orbital overlap happening like this, which is what we call end-on overlap, or we can have it happening like this. We're going to call that side to side. Those form two different kinds of bonds. Okay, so two kinds of covalent bonds that we're going to talk about making. One is called a sigma bond, which is akin to a single bond, and then there's going to be a pi bond. So let's kind of introduce this first here. Again, when we're forming a covalent bond, we're going to have two atoms overlap their orbitals, share a pair of electrons in that overlap region. And so if we want to make the strongest bond, the shape and the orientation of those orbitals is going to matter. Okay? So when we form single bonds, right? Single bonds, we're also going to call those sigma bonds. This is the Greek letter sigma, okay? So single and sigma sound the same, so that can kind of help you put those together. When we form single bonds, that happens from end-on overlap of hybridized orbitals. So sigma bonds are end-on overlap of hybridized orbitals. We're going to put this together in what I'm going to call a Mad Libs in a little bit, just to kind of have us understand how we're going to use and apply this skill. If we form multiple bonds are a combination of a sigma bond and then one or two pi bonds, depending on whether you're a double bond, which is going to be one sigma, one pi, or a triple bond, which is one sigma, two pi's. right? So if I'm just making a single bond, if you imagine my fingers are a bond here, a single bond is just one sigma bond. If I'm going to make a double bond here, okay, if I'm drawing two lines, one of those is going to be a sigma bond, one of them is going to be a pi bond. Pi bonds are formed from side-to-side overlap of unhybridized p orbitals. So this is a really important slide to kind of highlight the two kinds of bonds that we're going to see. Sigma bonds or single bonds are end-on overlap of hybridized orbitals. And then when we have pi bonds, they're side-to-side overlap of unhybridized p orbitals. That's a language you need to make sure that we know. So what do I mean by this Mad Libs thing? I don't know if you ever did Mad Libs when you were a kid. That's where you had a sentence where you had to fill in certain pieces. You had to either fill in, a verb or an adjective or something like that. Larry, sorry. So we're going to have a Mad Libs here. One of the things you're going to need to do is be able to use this Mad Libs language to describe a bond that I'm showing you in a covalent compound. Okay, so again, this says here, once you've determined all of the above, which is basically thinking about, and I don't have this slide here, we have to have a proper Lewis structure. We have to know the electron group arrangement because both of those are going to be important for figuring out hybridization. And then once we know hybridization, then that can allow us to direct the information to create a sentence to describe what that bond looks like. So I know this might look a little bit scary here. We're going to go through some examples to explain it. So first and foremost, every atom in a molecule is going to be connected by sigma bonds. Again, think sigma, think single. Okay? Here's how you describe any sigma bond. You're basically going to have two atoms that are part of that sigma bond. So for example, if this was carbon and hydrogen would go here. So I'm going to describe the two, list the two atoms. The blank and blank sigma bond is formed from end-on overlap. Remember, we said sigma bonds are end-on overlap of, and then we're going to say the type of orbitals. That's going to be the hybridization that we have, and then the kind of orbitals we have in that second atom. So as an example here, right, if we're talking about a carbon-hydrogen sigma bond, okay, carbon-hydrogen sigma bond is formed from end-on overlap of sp3 hybridized orbitals in carbon with the s orbitals in hydrogen. And again, noting that hydrogen atoms are never going to have hybridized orbitals. Also, if you're talking about sort of a piece that's only forming one bond, you won't have hybridized orbitals with that either, okay? Any atom that has more than one line connecting it to another atom, right, we're going to have double or triple bonds. These are going to be pi bonds. Okay, so here's how you'll describe any pi bond. Again, we need to say the atoms that are connected. We're going to say this atom and this atom pi bond is formed from side-to-side overlap of unhybridized p orbitals in this atom and this atom. Okay, so for example, if we had a carbon-carbon double bond, we would have one of those lines would be a sigma bond, but then we'd also have a carbon-carbon pi bond is formed from side to side, I don't have the word overlap in there, side to side overlap of unhybridized p orbitals in each carbon atom. Okay? One of the skills that you need to be able to do and apply is write one of these sentences for a bond that is in a molecule. Okay? All right, so I'm going to go through a bunch of examples here, hopefully to help solidify this. Right? So let's look at this guy. Let's look at ethane. This is called ethane, CH3, That's the Lewis structure that we could draw for this. Again, if we were thinking about the hybridization on that carbon atom, we would say that it is sp3, right? Kind of going through and reviewing. We'd have one s and then three p orbitals that we'd mix together to generate the 4 equivalent sp3 orbitals to be able to generate all 4 of these equivalent carbon single bonds there. So if we wanted to describe the bonding that we have here, notice here that we're going to have bonding between the carbon and carbon atoms, and then we're going to have bonding between the carbon and hydrogen. So there's actually 2 kinds of bonds that we have here. So there are 6 carbon-hydrogen single bonds. We also could say, again, these are sigma bonds. Single and sigma are sort of interchangeable. So the 6 carbon-hydrogen sigma bonds in CH3CH3 are generated when an sp3 hybridized orbital from carbon overlaps with an s orbital from hydrogen. This is the language you need to be able to provide to describe a bond for me. Okay, there's one other kind of bond that we have in this molecule, and that's the carbon-carbon single bond. Again, we could describe that as a sigma bond. So the carbon-carbon single bond is formed from end-on overlap of 2 sp3 hybridized orbitals, right? So again, I don't have the words is formed from. All right, so that's the Mad Libs language that we need to have. So that's for something that only has single bonds, so only sigma bonding. Let's move on to something that has double bonds here. Something that has double bonds will always have sigma bonding. We're always going to have single bonds, but then layered on top of that, you might have pi bonding. So again, here's a valid Lewis structure for CH2CH2. This is called ethene. Okay, so this structure here, again, we're going to have hybridization on this carbon atom that's sp2 because this code would be AX3, 3 things around that central atom. So if we think about the hybridization that we're going to have here, we're going to have 3 sp2 hybridized orbitals, and now we have 1 unhybridized p orbital that's left over. And that's the key. That's what's important here. We're going to have this unhybridized p orbital that we can use to generate our pi bond. So let's look at a structure of this and kind of map on what we see here. So what we have here is all of the sigma bonds, the single bonds. We're going to have 4 carbon-hydrogen single bonds. Again, those are sigma bonds. They're going to be generated when we're going to have the sp2 hybridized orbital from carbon overlapping with an s orbital from hydrogen. Okay? Now we have to think about, there's a double bond that we have there. That carbon-carbon double bond arises from 2 bonds. Remember, there's going to be the sigma bond and the pi bond. If there's 2 bonds, we have to have a sigma and then at least 1 pi. If it's a double bond, 2 pi's, as we'll see in a minute if it was a triple. So the 1 single bond, or the sigma bond, arises from end-on overlap of the 2 sp2 hybridized orbitals that we have in carbon. So we kind of didn't describe that, but that's this bond right there. The other bond, right, a double bond, is 2 parts, a sigma bond and a pi bond. The pi bond arises from side-to-side overlap of the 2 unhybridized p orbitals that we have that were left over on each of those carbon atoms. Wow, I know that was a lot, but hopefully you can see that when we have this double bond here between carbon and carbon here, we're going to have a sigma bond and then this pi bond that we have here. All right. One more example here to kind of like expand on that. So again, let's just look at this picture here, thinking about this CH2CH2, again, this ethene. Here we can see the sigma bond, which is the sp2 hybridized orbital overlap. We're going to have that end-on overlap. So again, these 4 carbon-hydrogen single bonds, we're going to have that sp2 hybridized orbital in carbon overlapping with the s orbital in hydrogen. Same words here as on the last slide, just looking at a different picture here. And then when we have the pi bond here, that pi bond arises from the overlap of the unhybridized orbitals in carbon, those unhybridized p orbitals. All right, so just another picture, not anything new there, just a different picture that kind of represents that same information. All right, one more example here. What if we had a triple bond between carbon atoms there? So not a single bond, which was ethane, not a double bond, which was ethene. We've got a triple bond, which we call ethyne. You'll get to that when you take organic chemistry. But this is, again, we need to start with a valid Lewis structure that shows us what we have here. That code would be AX2 for these carbon atoms. 2 letters mean we're going to mix and generate 2 hybrid orbitals. So the hybridization on that central carbon atom is going to be sp. So again, we're going to be mixing 1 s orbital with only 1 of the p orbitals there to generate the 2 sp orbitals that we need to generate the 2 bonds, one between carbon and carbon, one between carbon and hydrogen. And we've got 2 unhybridized p orbitals that are left over. Those are going to be useful to form 2 pi bonds. All right, so putting this together here, We're going to have the 2 carbon-hydrogen single bonds. Those are, again, the sigma bonds. We're going to have the sp hybridized orbital in carbon overlapping with the unhybridized s orbital from hydrogen. You don't need to say unhybridized with that hydrogen orbital because we always know that's the case. Again, making that triple bond, we're going to have actually 3 things that we need. The first is that single or that sigma bond that we're going to have from end-on overlap between the sp hybridized orbital in carbon and one carbon atom with the sp hybridized orbital of the other carbon atom. And then we've got 2 pi orbitals, right? Side-to-side overlap of the unhybridized p orbital. What's interesting is one of them is going to be in this direction. Another one is going to be 90 degrees to that. So here's the 3 bonds in our triple bond. End-on overlap of hybridized sp orbitals, side-to-side overlap of unhybridized p orbitals, and then another side-to-side overlap of unhybridized p orbitals. I know that's a lot. Take a look at these pictures and see if that makes sense. Same information here, just a different picture to look at. And again, we can see here that we've got, here's our sigma bond. Here's another sigma bond here. Those are the single bonds that we're connecting. And then when we have to map in our pi bonds, that's side-to-side overlap of those unhybridized p orbitals. All right, so I know that was a lot, but what is key to this skill is being able to describe, using that Mad Libs language, what this bond is made of. End-on overlap, side-to-side overlap. Or you'll see some problems where you actually have to count the number of sigma or pi bonds that you might have in a given molecular structure. Last little piece to kind of highlight here. All right, let's think about what happens if we want to do bond rotation. So I want you to imagine if you were connecting your fingers and you were holding them together with magnets like a little bond, okay? When we're like this and we're I can rotate my fingers like this. So we can rotate sigma bonds, right? But if my fingers are connected together with little magnets and I'm making a pi bond, I can't rotate like this without breaking the magnets. What that means is we have what we call free rotation about sigma bonds. So if I'm doing this kind of a bond, I can rotate my fingers. I can move my fingers without breaking the magnets, without breaking the bond. But pi bonds have what we call restricted rotation. So if I'm making a pi bond and I've got magnets that are kind of holding my fingers connected, right? I can't move my fingers unless I broke those magnets, okay? So we have restricted rotation about pi bonds. So that's just one of those things I want you to know, that there is free rotation about sigma bonds. We have restricted rotation about pi bonds.